All right, mathletes, here we are at A9.1. We're dealing with nth roots and rational exponents. So first thing we're going to talk about is simplifying radicals. Remember, when simplifying radicals, we're looking for those perfect squares. If it's a radical 2, in perfect cubes, if it's a cubed root, and a fourth root, we're looking for powers of 4 there. So for the square root of 48, I'm thinking about perfect squares that are going to go into it. Things like 4, 9, 16, 25, and things like that. For this one, I notice that 48 is a multiple of 16 times 3. Choosing 16 because it's a perfect square. I know 48, there's other multiples. I could do 12 and 4. But I always like to pick the largest perfect square I can pick out, because really 12 is 3 times 4. So there'd be another perfect square I could pull out. So after I break this down, I kind of think of it as square root of 16 times the square root of 3. Square root of 16 can simplify to be 4 square root of 3, and just leave that in radical form there. So cube roots, my perfect cube roots are going to be 8, 27, and 64, and numbers like that. So 48 is a multiple of 8 times 6. So I rewrite 48 as a composite number. And then I think, all right, cube root of 8 times the cubed root of 6. So this can be reduced to 2. This will stay in our radical. So that is simplified form there. Now 48. Here I'm thinking about perfect fourth powers. I go into 48. Well, 16 is going to come up again, times 3. Fourth root of 16 times the fourth root of 3. We're going to get 2 times fourth root of 3. All right, so that's our simplifying radicals. Next property of radicals that we'll want to know is, just like how we simplified them up, they can be broken up into individual terms and multiply together. Same thing with division. We can think a radical of a rational can just be the radical of the numerator divided by the radical of the denominator. And as far as the sequence of the powers that we do, we can take the power inside our radicand and multiply that out, or we can also do it after and put it on the outside, so that order won't matter there. So some properties that we should make sure we have in our notes as we're simplifying these will be important to use. So first example, so if we want to simplify these radicals, anything that are for part A, that's a perfect 4 power, we're going to want to make sure we factor that out. So again, I'm thinking about things that are perfectly into 4. So I know that 16 can be 2, 2 to the 4th power. So 16 times 2 is going to be equivalent to 32. Now, x to the 13th, to write things that are going to be perfectly to the 4th power, I need my exponent to be in a factor of 4. So I'm going to think of this as x to the 12th, because that's a factor of 4, 4 times 3. And then I know that to get to x to the 13th, I'm going to do it times x. And y to the 12th is always already a perfect power. So as I'm thinking about these fourth roots, now I'm going to break it down. The fourth root of 16 will simplify. The 2 is going to stay. The fourth root of x to the 12th is going to be able to simplify. This x is going to stay, and then I'm going to have the fourth root of y to the 12th, because that'll simplify, and then everything that will stay in our radical, our fourth root, is going to be 2 times x, being the ones here that weren't our perfect 4th power things. Well, 16th to the 4th root, that is going to be 2. x, fourth root of x to the 12th power is going to be x cubed, and the same logic for y to be y cubed, and then we have our root here, 2x. Make sure when you're writing your radicals, don't forget your indexes here. But this is our simplified form here. For the next one, b, we have, so sometimes it's, to simplify them, it's going to be better if we combine them. So first I'm going to multiply these together. So 5 times 20 is 100. X squared times x to the third is x to the fifth. So square root of 100, I should know, is 10. And then I have, again, I think of the square root with the power of 2. So I want to write x to the fifth as a product of things that could be a factor of 2. So it's x to the fourth times, and then x to the fifth is going to be the one term that's going to end up staying underneath my radical. Well, the square root of x to the fourth is going to be x squared, and then I'm just left with the square root of x. That is my simplified form. All right, so here on C, we can see that sometimes it's going to be advantageous for us to simplify and reduce here. So I'm looking at my coefficients. 72 divided by 9 is going to be 8. Well, x divided by x over 4, you can think of it as x over x times x times x times x. So that's going to simplify to 1. So then I get 1 over x cubed. So I'm going to have an x cubed in the denominator. And same sort of logic for my y's here. Y divided by y to the 7th is going to be y to the 6th. So this is still all underneath my radical. So I can individualize it and think of each term as the cubed root of 8 over the cubed root of x cubed and the cubed root of y to the 6th. So as I reduce this, the cubed root of 8 is 2. Cubed root of x cubed is just x. And the cubed root of y to the 6th is y squared. And if this is kind of confusing to you, you can always think of it like this, that if you have y cubed and then you have y cubed, well, this is all equal to y to the 6th. So what you get kicked out is a y times y, or y squared. All right, so D here, multiplying through. So with radicals, you can multiply coefficients together and you can multiply radicals together. So kind of group-like things. So 5 times negative 3, I can multiply together, and I'm going to get negative 15. And because they both have the same index of a 2 here, square root of 8 times the square root of 3 is the square root of 24. So from here, I still want to reduce this. I'm looking for perfect squares. I go into 24. I'm going to get the square root of 4 times the square root of 6 is 24. Square root of 4 is 2. And now I can combine that with 15 and get this to be negative 30 times the square root of 6. I've simplified it there. On the next one, multiplying two binomials here. Again, we got to make sure we multiply throughout. So I got to multiply negative 5 to both of these and negative 2 to both of these. So as I multiply the negative 5 through, negative 5 times negative 5, or square root of 5 times the square root of 5 is going to be 5. And then I get plus the square root of 5 times 3 minus 2 square roots of 5. Doing this math, negative 2 times this, I get minus 6. Typically, I'm going to want to write this with my coefficient in front. So I'm going to group my like terms. I get 5 minus 6. Those are my integers, and then for my irrational roots, I get plus 3 square roots of 5 minus 2 square roots of 5. Now simplify, I get negative 1. 3 square roots of 5 minus 2 square roots of 5. I'm going to get minus square roots of 5. You can think of it as 3 of something minus 2 of the same something. Well, you get plus 1 of those left. All right. So for the next one here, we got to talk about rationalizing the denominator. When you're rationalizing the denominator, we don't like radicals in the denominator, so our trick is multiply by the same thing as our denominator if it's just a single term. So I'm still utilizing this idea that I'm multiplying by 1, so I'm going to be smart about the one I choose and multiply by square root of 2 over the square root of 2. So as I multiply this through, I get square root of 2 in the numerator, and the denominator is square root of 2 squared, or just 2. So now, because this denominator is a rational number, it's 2, it's been rationalized. All right, so here on the next one, I got to think, I'm trying to get a perfect cubed root here. So I know that 8, the cubed root of 8 is going to be equal to 2, and that would rationalize my denominator. So to get this 4 to be 8, I want to multiply it by the cubed root of 2, and then I want to make sure this is, I'm just multiplying by 1, so I'm not changing the equality here. So I get 6 times the cubed root of 2 all over, well, it's going to be the cubed root of 8, which will end up being 2. And then I look at my coefficients, 6 and 2. Well, 6 divided by 2 can be reduced, so I get 3 cube roots of 2. So there's that rationalized. For C, we got to utilize a conjugate here. So in order to do this is, we want to multiply this by our conjugate. So it's very similar to how we did it with complex numbers. So our conjugate of our denominator is 5 plus the square root of 2. Notice this sign changed there. Again, I'm multiplying by 1 to preserve the value here. So I do 5 plus the square root of 2, and now distribute. The numerator is nice because I just get 5 square roots of 3 plus the square root of 6. This square root of 3 and square root of 6, adding them together, there's nothing we can do. That's as simplified as it gets. In the denominator, we double distribute, so we get 5 times 5, 25. 5 times square root of 2, we get plus 5 square roots of 2. And then we get minus 5 square roots of 2. And then we're going to get a minus square root of 2 squared. Well, these will cancel out, as they should, and that's the whole purpose of this, so we get rid of our radicals. You kind of see our difference of squares falling out here. So then what we have is we get 25, and then we have minus square root of 2 squared is 2. So we get 25 minus 2 there. This is 5 square roots of 3 plus the square root of 6. And just simplify the denominator to be 23. 5 square roots of 3 plus square root of 6. All right. So these are some principles as we're simplifying rational exponents. We got to remember that fractional exponents or rational exponents, that they're very similar to our roots. So notice that the power, the numerator, is to the power. You think that the numerator, when it's larger, as a fraction, it makes things bigger. as do powers. And then our denominator here in our fraction is n, and that's our root. And typically dividing our number in our denominator of our fraction is going to make things smaller as we do think of our roots. So 8 1/2 is the same thing as the square root of 8, which is equal to the square root of 2 times 4 times the square root of 2, which is all going to be 2 square roots of 2. Okay? And 2 to the 4/3, if I want to write this just as a similar to this notation here, I'm going to get 2 to the 4th and cubed root there. And I can simplify this by doing 2 to the 4th, which is going to be 2 times 2 is 4. We get the cubed root of 16, which can be written as the cubed root of 8 times the cubed root of 2. So this simplifies to 2 cube roots of 2. Let's look at some other simplifications here. 4 to the 3/2. So we can think of this as do the square root of 4 to the 3rd power. Well, that's 2 to the 3rd, which is equal to 8. Okay, so do the similar thing. Always try and do your roots first. So -8 cubed root, and then to the 4th power. -8 cubed root is -2 to the 4th power. -2 to the 4th power is going to be 16. Then you have 32 to the 5th root, then to the -2 power. Well, 32 to the 5th root is 2, the -2 power. Remembering a negative power is just going to drop things into the denominator, or they reciprocate them. So I get, this is equivalent to 4 to the -1 power, because that's 2 squared. And as I reciprocate that, I get 1/4 as my final answer. All right, let's look at some other examples, or last page here. So remember, when you're simplifying exponents, if it's x squared times x to the 5th, it's x to the 7th. But if you have it to the parentheses, it becomes 2 times 5, and you get x to the 10th. So for D here, again, I'm going to think of it as a cubed root. So I get 27 over 8, cubed root it, and take it to the -4th power. So the cube root of 27 is going to be 3, and the cubed root of 8 is 2. This is all to the -4th power. So taking the 4th power to all these, I get 3 times 3 is 9, 9 times 9 is 81, 2 times 2 is 4, 4 times 4 is 16. This is still to the -1 power, so I reciprocate it, and I get 16 over 81, flipping our terms there. So that's simplified there. For E, remembering these rules, I'm going to distribute, so I get x to the 1/3, y to the 1/3. I get x to the 2/3, and y to the 4/3. Well, now I want to group like terms, so my x's, I add my powers now, and I get x to the 3/3, and I get y to the 5/3. Well, this is just going to be x to the 3/3 is x, and then I'm going to leave this as y to the 5/3. That's going to conclude our notes tonight. Make sure you highlight any questions and bring them to class tomorrow. Thank you.